Welcome back. Okay, in the last lecture, we derived the wave equation for a vibrating guitar string from scratch from F equals ma physics, literally just, conservation of momentum of a little infinitesimal section of guitar string vibrating up and down, being forced by its own tension, essentially the tension in the string. So we derived this equation from scratch, where the wave speed c is related to the material properties of the guitar string. C is literally the square root of the tension divided by the linear density. So increasing the tension increases the wave speed, which makes higher pitched sounds. Decreasing the tension makes it lower pitched. I massively detuned my guitar last time, but it's back to in tune. And the linear density, a thicker string, a thicker, heavier string like the low E, will have a lower wave speed because it has a higher rho than a thinner, lighter high E string, right? So this one, the low one, has a bigger rho, smaller C. The lighter one has a smaller rho, higher C. And that translates to either a lower pitch sound or a higher pitch sound. So what we're going to do today is from this wave equation, we're now going to solve this for some specific boundary conditions, literally for this guitar boundary condition where it's pinned kind of here and here at the bridge and at the neck. And then we're going to analyze what happens, to this wave equation. What happens? What are the solutions of this wave equation, and how does that translate into intuitive things we know, from music, from sound, from things like that? Okay, so that's all coming up, and we're going to solve this using separation of variables, one of the most important solution techniques for partial differential equations. I want to point out, I hope you appreciate, I hiked my guitar up 3 miles from home to film today, so I hope you appreciate the dedication. I thought about just playing air guitar, but I figured this would be a lot more interesting. Just preface at the very beginning, I am a complete amateur novice. I know zero music theory. My wife likes to joke that, all I know is string theory for the wave equation and the string. I don't really know any music theory. But I do think that this is a really intuitive kind of example because music, much like mathematics, I think resonates very much with the kind of logical part of our brain, but we also know when it feels right. And so that meeting place of kind of thought and feeling, I think, is very much shared between mathematics and music. And in fact, there are deep, deep connections between music and mathematics that people have been exploring and uncovering for hundreds of years, for centuries, if not millennia. So even if you go back, this is a little bit of just a history digression, but I think it's interesting. If you go back to Tycho Brahe and Kepler, before Galileo, before Newton, before we knew about F equals ma, and before we had proven that the sun was the center of the solar system, when things were still speculative and people didn't understand why the planets behaved the way that they did, there was a theory, and Kepler held on very strongly to this theory, that there were harmonic patterns in the motion of the planets and the motion of the stars, just like musical patterns and layers that define musical composition. They believed that there were these patterns in the stars and the heavens and the planets, and that musical composition was perhaps divine and definitely had an impact in our daily lives, right? This is astrology, from the olden days. It always had this flavor of, one part mathematics and one part music. Just fascinating, I think. Oh, and in lugging my guitar to work today, I was thinking back, a friend of mine taught me a new word called busking. So busking is when you bring your guitar or musical instrument and you play in public, in a public space. And I think this is super fun. Busking comes from the Spanish word buscar, which means to seek, to seek out or something. And so we are all, in some sense, busking and buskers because we're all seeking knowledge. This is a very, very meta, 2 steps removed online YouTube version of busking, I suppose. Okay, good. So I'm going to jump right into this. We're going to solve this equation using separation of variables. Maybe I'll just write it here, separation of variables, which we've already seen before when we solved Laplace's equation for the heat distribution in a rectangular metal plate. Here we're going to solve for kind of, the vibration, the motion of this string, where it's pinned in two locations at x equals 0 and x equals L. L is the length of my string. And so again, for a partial differential equation to be well defined, we need to define its boundary conditions and its initial condition. So I'm going to do that here. I'm going to say, just to be very, very clear, u of x and t is the height of the string, the height or the displacement of that string, the displacement of the string. And it's going to be a function of x, the position along the string, and in time. It's going to be oscillating in space and in time. And our boundary conditions are essentially u at x equals 0 for all of time is going to equal 0. So we've essentially pinned the string in one position up at the neck, and that is going to be a 0 displacement for all time. This is at the neck. And similarly at the bridge, at the other end of the string, u of, sorry, it's so squeaky, is also equal to 0. So at length L, for all time, it's also pinned in that location, but it can kind of do whatever it wants in the middle. Okay, so I can deflect the string, I can pull the string with my finger and make it a little shallow triangle. That's totally fine as long as it stays pinned at both of the boundaries. And then the last thing I need is my initial condition. Maybe I'll switch colors so it's not so squeaky. Oh, still squeaky. My initial condition is going to be u at x at time 0. So now remember my boundary conditions are for all time at spatial boundaries. My initial condition is at a given time, at my initial time t0, at all of the positions x. I'm just going to define the displacement at time 0 to be some function of x. And this function of x could be, that I take my guitar string and I, essentially pull up on the guitar string in one place and then I let it go. That could be my f of x, is that it's this little triangle from me pulling up, and about to, with my pick or with my finger. So I have boundary conditions and initial conditions, which make this a well-posed partial differential equation. It's a linear partial differential equation, which means that superposition holds. It means that if I have multiple solutions and I add them up, if I have multiple solutions that satisfy my boundary conditions and I add them up, then there's still going to be a solution of my partial differential equation. That's nice. And we're going to solve this using separation of variables just like we did before. So I'm gonna jump in. So our separation of variables assumption, the basic assumption here, is that u of x and t, my function of space and time, is separable, which means that I can write this as a product of a function just of x, f of x, times a function g that's just a function of time. So this is the basic assumption of separation of variables, is that I can say that my solution, which varies in space and time, remember that guitar string is vibrating in space and in time, but I'm going to assume, this is an assumption, that it can be written as a product of a function just of space times a function just of time. And when we plug this into our PDE and go through all of the steps, we're going to see if that assumption holds and if we can get a solution that satisfies these boundary conditions and initial conditions. Good. So that's what we're going to do. And maybe I will just start writing out what the derivatives are. I think that's a good place to start. We're going to plug it into this PDE. So we need to be able to compute UTT and UXX. Pretty simple. So UTT is just the second partial derivative of this with respect to time. So that's f of x times g double prime t. Good. And similarly, UXX is f double prime x times g of t. Pretty simple stuff here. Okay, and because we know that ut equals c squared uxx, I can use these expressions to essentially say that fx g double prime t equals c squared f double prime x g of t. Okay, good. And so now, just like we've done in the past, what we're going to do is we're going to collect all of the functions of x on one side and all the functions of g on the other side, and we're going to try to turn those into ordinary differential equations just of x and just of t. Okay, so we're going to try to take this spatial temporal problem, this function of two variables, x and t, and break it down into just a problem in x and just a problem in t that we can solve using our kind of basic ODE technology that we are very comfortable with. Okay, and I always forget where I should keep my c. Should I keep my constant on the x terms or on the time terms? I think I'm going to keep I think I'm going to move my c's over. So I think what I'm going to do is I'm going to say I have f double prime of x over f of x. I'm going to divide both sides by f, and I'm going to divide both sides by g, and I'm going to divide both sides by c squared. So this equals 1 over c squared g double prime t over g of t. You can pause the video, slow it down, whatever, but all I've done is I've divided both sides by f double prime, by g double prime, and divided by c squared, so that the c squared is now with my functions of time. And this is where, in the last video where I did separation of variables for Laplace's equation, I made a really big point of emphasizing that if I have a function that's just a function of x, and I have a function that's just a function of time, and they equal each other, then they both have to be equal to a constant. This has to equal some k, I should not spell constant with a k, but this is a constant. Okay, this is a constant, k. Okay, so, and that's again because this is just a function of x and this is just a function of t, and for those to be equal to each other, it has to equal some constant k. And maybe what I'll do, because that these are going to be eigenvalues, I'm just going to call that constant k some constant lambda. Okay, some constant lambda. And in fact, I'm going to make it lambda squared because I know it's going to be a positive constant. We'll get there. Maybe I'll just call it lambda. Good. So I should point out, okay, I'll do, the next step is going to be solving, just taking f double prime x over f equals lambda and solving that ordinary differential equation in x, presumably with these boundary conditions, and then doing the same thing for the time ordinary differential equation and then combining those. That's what we do in separation of variables. I'll point out, I mentioned in the last video that the wave equation is something I actually don't usually dive too much into depth in my class. It's something, I've spent a lot of time over the years contemplating the wave equation. It's never been my favorite PDE that I felt really, really comfortable with. It's super important. It's everywhere. And over the last few days, I have just been, wandering around like a planet. Planet means wanderer. So I've just been wandering around, listening to guitar music and thinking about the wave equation and its solution. And when I derived this out as kind of a test run of this video, I got all the signs wrong. My C's were all in the wrong place. So I just want you to know that if it looks like, if it goes really smoothly, it didn't the first time. And if it doesn't go very smoothly, you are forewarned. Okay, this is the kind of thing you got to be really careful to keep track of the signs and where the C's are and all of that stuff. And for me personally, the only way I can keep track of it is to have some idea of the physical intuition of what I want my solution to look like. So maybe before I solve this, I'm going to just go back to the physics here. we have a guitar string that's pinned in two places at the, one condition x equals 0 and another x equals L, the length of the string. The only solutions that can satisfy those two boundary conditions essentially have to be sine waves that have, a period of L, something like sine of, x pi over L, or sine of 2 pi x over L, or 3 pi x over L, or 4 pi x over L. Those are the only, basic solutions that can satisfy these two boundary conditions. And so I kind of already know that my functions of x, my f of x, are going to be sines with that period. And so that's going to help me figure out, should my lambda be positive or negative, things like that. So let's hope I get it right. If I don't, we'll fix it. Good. So now what we're going to do, so step 0 essentially was, the basic assumption of separation of variables. Step 1 is, computing all of the derivatives and getting to this point here. So step 1 is computing all of these derivatives and kind of arriving at this basic expression here. And now step 2, I'm going to break it up into two parts. I'm going to solve the ODE for the functions of x, and I'm going to solve the ODE for the functions of time. So, and let's call this 2a, because there's two parts to this. What I want to point out is I always want to pick the one that's easiest to solve first, where I have more information. And if you notice here, it looks like my boundary conditions are pretty simple. I have, fixed pinned boundary conditions at x equals 0 and x equals L. And so I'm pretty sure my functions of space are going to be sine waves with that length L period. So I think that it's going to be easier to solve these f equations first. And then once that determines uniquely what this constant is, again, this constant is going to be determined somehow by this length L. Once I determine what that constant is and what these solutions are, then I can solve for how those vary in time. So I'm going to start with my functions f. That's just generally speaking a good idea to start with the easy stuff first. And so here we have an equation that's something like, f double prime x over f of x equals, maybe I will call this lambda squared, but I think I remember what issue I had when I was deriving this a couple of days ago, is that I am used to this constant being positive, this lambda squared. And when I used a positive constant here, let's say this is lambda squared. When I used a positive constant, I got the wrong solutions to this ordinary differential equation. I'm looking for sines and cosines in x, and I think I got like exponential functions in x, which is not right. And so I had to remind myself that this could be a negative constant. This constant that both of these equal, this can totally be a negative constant. So this is going to make my life a lot easier. And I think what you should do for those of you at home is you should try this for a positive constant and work out what those solutions f of x are, and convince yourself that you can't possibly satisfy these boundary conditions with the exponential functions you get with a positive lambda squared. But when you use negative lambda squared, we're going to get sines and cosines out, which make it so we can satisfy these boundary conditions. So I'm kind of skipping a couple of minutes of existential crisis for you, and we're just going to use the prior knowledge I have that this should probably be a negative constant. But you could figure this out yourself. This constant at this point is completely undetermined. It could be anything you like. And I'm using lambda squared because this is a second order equation, and it's just going to be easier to have it be lambda squared. You could just call this some constant k and work it all out yourself. Okay, so what we have here, and I'm just going to switch back to yellow, is that we have f double prime plus lambda squared f equals 0. And since this is not a partial differential equation, this is an ordinary differential equation. It has one independent variable, x. And so this ordinary differential equation is easy to solve. We know how to solve second order linear differential equations. This is essentially the equation for a mass on a spring. And this lambda squared is the square of that spring frequency, the frequency of oscillation. So that's, again, why I needed this to be negative, so that when I multiplied F and added it, I got a spring equation that has a plus and minus I omega eigenvalue, okay? And so essentially, we know that this is going to have solutions F of x equals, and how do I want to write this? This is going to have F of x equals some constant, I'll call it, alpha, cosine of lambda x plus some other constant beta sine lambda x. Okay, good. So this is just what happens when you solve this differential equation. You get a cosine and a sine component. Again, you can go back to your kind of basic linear ordinary differential equations to solve this. This is the solution. And what we know is that the only way that this function f can satisfy both boundary conditions being 0 at x equals 0 and x equals L is essentially, cosine is not going to be ever 0 at x equals 0. So the only way we can solve this is to have the alpha, all of these terms equal to 0, no cosine part, because cosine of 0 is always equal to 1. Okay, so it can't satisfy this left boundary condition unless alpha is 0. And the only way that sine of lambda x can satisfy this boundary condition is if lambda equals pi over L times some integer n, where n equals 1, 2, 3, dot, dot, dot. It could also equal 0. Let's put 0 in there. It could be 0, 1, 2, 3, dot, dot, dot. It could also be -1, -2, -3. That's all fine. But the only way that this can satisfy the 0 boundary conditions at x equals 0 and x equals L is if lambda equals pi over L times some integer. Okay? And so essentially what we get is that f of x equals, let's just call this beta n, because there's going to be a constant for every integer n, beta n sine of n pi over L times x, where lambda equals pi over L. Pi over L times n. Okay, good. So we have solved kind of half of our ordinary differential equation. So we've solved the functions of x. The only way they can satisfy these boundary conditions is for very particular lambda. Remember, special values are eigenvalues. So these lambda are eigenvalues of this ordinary differential equation, f double prime x plus lambda squared f of x equals 0. This ordinary differential equation has eigenvalues plus and minus I lambda. And that gives cosine of lambda x plus sine of lambda x type solutions. The sines are the only ones that can satisfy the pinned boundary conditions here. And they can only satisfy it for very special lambda, for very special values, so that that sine is equal to 0 at x equals 0. That's true for any lambda. But for it to be equal to 0 at x equals L, then lambda L, sine of lambda L, has to equal 0. And that has to be sine of lambda L, has to be some integer multiple of pi. Okay? And so essentially this is the solution for all the functions in x. Good. And so we've done two super important things here in this step. We have determined that the only spatial solutions to this partial differential equation can only be built out of sine functions in x. And we've also determined, out of all of the possible constants that these could equal, lambda has to be a very, very special constant, an eigenvalue constant, given by pi n over L, where n is an integer and L is the length of my string. So we've determined that our eigenvalue has to be pi n over L to satisfy these boundary conditions, and that our functions of x are sines with that frequency. Good. So that was, believe it or not, that was the easy part. And now for 2b, we're going to solve the same equations in G for the temporal dynamics, for these G of t coefficients here. So let's do that. And actually, this one's not going to be super hard now. I just want to make sure I give myself space to do it. So maybe I'll just do it right here. So for 2b, we're going to be solving now my G equations, which are going to be something like G double prime equals minus c squared lambda squared G. Okay, and if I rewrite this, I can say that that's G double prime plus c squared lambda squared G. Pretty simple. Okay, and now this is kind of nice because this equals 0. This is basically the same type of equation. This is also an ordinary differential equation that has the same form as a mass on a spring. And now instead of the frequency being lambda, the frequency is c times lambda here. Okay, so similarly, my G of t's are going to be equal to some other constants. I don't know what to call these. Let's call them, I don't know, k times cosine of c lambda t plus some other constant c times sine of c lambda t. Okay, good. Now we can essentially fix this lambda. We know what lambda equals. It's pi n over L. So this is, c times pi times n over L times t. That's going to be like the frequency of how this string is oscillating in time. And again, if I pluck a guitar string, it's generating acoustic waves based on its oscillating frequency. So this frequency here is going to be directly tied to the frequency that I hear when I pluck a guitar string. So it's going to depend on this c and on this lambda, which is a function of the length of the string, and n, which are the harmonics. So we'll get to harmonics in a minute. And so now how do I figure out if this is cosine or sine or some combination? And I think what I would argue is that because this thing starts with an initial condition, u of x comma 0 at time t equals 0, I'm really only considering the cosine portion of this because sine of c lambda t is equal to 0 at time 0. So I'm only going to use the cosine portion of this to determine to satisfy my initial conditions. So I'm only going to be looking at this portion. And I'm going to explicitly plug in my lambda here, and I'm going to say this equals, I've got my cosine of n pi c over L t, and this constant k, I'm going to say that there are n of these constants for every integer n. For each of these lambda n, there is a constant outside of that cosine. Good. And if you like, this constant is basically going to be determined by this Fourier transform here. So I'll get back to that in a minute. Okay, so this actually ended up being simple. Now that I had fixed this lambda from my functions of x, I use that lambda in my ordinary differential equation for my function of time. I solve it out. I get that it also is sines and cosines. And the only way I'm going to be able to satisfy this initial condition at time 0 is through these cosine components that I have here. And so now, if I combine these two equations, I essentially get my answer, which is, let's see if I can not botch this. It should be pretty simple. U of x and t, remember, it's the product of all of these. For every n, for each integer n, it's the product of this sine and this cosine And I add up all of those solutions for all n, because this is a linear PDE, so all of those solutions are solutions, and when you add them up, it's still a solution. So this is equal to the sum, let's say from n equals, 0 to infinity, and I'm going to just combine these two constants, my beta n and my kn. I'm going to multiply these together, so that's just some constant n of, sine n pi over Lx times cosine n pi c over Lt. And this is the solution of my wave equation. That was the worst star I've ever drawn. So this is the solution of my wave equation. So u of x and t, the displacement at every point x at every point time, is given by this infinite sum of the products of sines in x that satisfy my boundary conditions and cosines in time. And if you like, what we're going to do, the way that we determine these coefficients is we use our initial condition. We say time equals 0, so all these cosines just become 1. Cosine of 0 is 1, so these go away. And we basically say, u of x at time 0 is equal to f of x is equal to the sum of n equals 0 to infinity of cn sine n pi over Lx. And so that literally means that these CNs are the Fourier coefficients if I Fourier transformed my initial condition f. So these CNs are literally f hat. They're the Fourier transform, the discrete Fourier transform of this initial condition over that domain 0 to L. Okay, and if that was a little fast for you, you can go back to that video on separation of variables for the heat equation, or you could go to my lecture on the discrete Fourier transform. Like, this is literally the definition of the Fourier transform, where these guys here, this is literally my f hat Fourier transform, the Fourier transform of f. These are my Fourier coefficients of f of x. That's it. That's the whole story. That's how you solve the wave equation using separation of variables. It's actually quite simple. You assume that you can split your function into a product of a function of space and a function of time. You plug that into this partial differential equation and take all the derivatives and get, a relatively simple expression and collect all the terms in x and all the terms in time. And because those equal each other, they have to equal a constant. And at this point, we don't know what this constant is. It's just some constant k. But then what you do is you try to solve this ordinary differential equation for just my spatial variables. F double prime x over f of x equals some constant. And the only way that that can satisfy my boundary conditions is if this constant is a very, very special number, pi over L times an integer. The only way that we can satisfy this boundary condition is if lambda is pi over L times an integer. So those are my eigenvalues of this ordinary differential equation, or of this partial differential equation. The corresponding eigenfunctions of this are these signs with that wave number, with that lambda wave number in x. Then you do the same thing for my ordinary differential equation in time. Now that I have determined what that eigenvalue lambda has to be to satisfy my boundary conditions, I have to use that same one for my ordinary differential equation in time. So now I get these sines and cosines in time with a slightly different frequency. And when I combine those two solutions, when I take their product here and I add them up for all integers n, I get the solution of my partial differential equation. And what that means physically is that the solution of this partial differential equation, I basically take my initial condition and I decompose it into a bunch of signs. I take its Fourier transform to find out how I can add up infinitely many signs with period L, all of my signs with period L. And that determines this, this constant C for my solution. And so then each of those independent kind of harmonic components, each of those independent sine waves, we're literally saying if I have some initial condition, like maybe what I do is I pull up the guitar string, with my finger, and I make this little triangle that is equal to the sum of this sine wave plus this sine wave plus this sine wave, and so on and so forth. This is the n equals 1, 2, 3, 4, and so on and so forth. And the coefficients Cn are given by the Fourier transform of my initial condition. This is f of x. Then each of these components, these wave components of my initial condition, oscillate at a different frequency. So this n equals 1 component oscillates at a frequency n pi c over L. The n equals 2 oscillates at twice the frequency, n equals 3 at 3 times the frequency, and so on and so forth. And so essentially, this vibrating guitar string is causing pressure fluctuations in the air that it's sitting inside of, and that's what's creating the acoustic waves that are radiating away from this that you can hear when someone plays the guitar or when someone plays the piano. Okay, it comes from literally from this frequency here. This is going to be the frequency of sound that you hear. Is this n pi c over L. And so now we actually see very clearly, and I'll pull out the guitar again for this, is we knew that the wave speed depended on things like the tension in the string. So, if I increase the tension, it should increase the speed. And so now we know directly that increasing the tension will increase the frequency of acoustic waves, because this is the oscillation in time that's creating those acoustic waves. Kind of how fast this thing is flapping in time is n pi c over L. So increasing C by having a smaller string makes a higher pitched sound. Increasing C by increasing the tension also increases the sound. But the other thing that could, increase the frequency, the pitch of the sound you hear, is changing L. So if I make L smaller, if I cut L in half, this frequency should double. So if I take my length and I pick the middle point of the length, I think you can see this, the middle point here, this is the 12th fret, the middle point is twice the frequency. Okay, so changing L, if I cut L in half, if I pin this thing so it's half the length, it's going to be twice the frequency. Or I could increase the tension by a factor of, I guess in this case, 4. If I made 4 times the tension in the string, it would double the frequency. Or if I made it 4 times less dense, if I ever picked a material that was 4 times less dense, or I made it 4 times smaller, those would all have the same effect of changing the frequency of the sound. Something else I think is kind of neat is if you picture, I'm literally like pulling this guitar string up, so it's a little bit, like a very, very shallow triangle when I pull it up, and that's my initial condition, and then I let it go. You can picture the sum of all of these waves oscillating in time, kind of the amplitudes are oscillating in time to generate that sound. And so if I just very lightly hold down the string at just a random location, you hear that it's really damped. You don't hear anything that sounds nice like a chord, it just sounds damped. But there are some very special locations where some sound does come through. Here's one, and I believe this is a third harmonic. It's a third of the length of the string. So, some of these waves have a node, a 0 point at that location, and so they are not affected by me damping at that location. And you can hear this really, really clearly if I put my finger very lightly on the 12th fret. You can see that most of the sound is coming through, and it's a little bit higher pitched. That's because all of the even ends, n equals 2, n equals 4, n equals 6, all of those even ends are being able to come through. Even though I'm damping, I'm kind of like holding a little bit of a damper at this point, all of the even end sine waves are not affected because they perfectly kind of pass through that 0 point where I'm holding my finger. Whereas if I pick a random location and I put my finger there, I'm kind of killing all of the waves and I'm killing all of that sound. Maybe this will make more sense if I pick one string. And it's twice the frequency, n equals 2. So that's kind of cool. Anyway, this is just an example of how you can get some intuition. So I always like to think about these kind of wave physics with an intuitive example. You could pick Maxwell's equation. You could pick ripples on a lake. I like the guitar string because I think it's very intuitive. How these sounds are being generated. You can put your finger in different places to change L. You can increase the tension or decrease the tension. You can go to a string that has lower density or higher density, and all of those change the frequency of the sound. Good. Yeah, one last thing I want to show you, and this is going to end up being an entire additional lecture. So I'm going to very likely have a whole lecture on the method of characteristics, which is a very, very, very important idea in these. This is called a hyperbolic partial differential equation. So this is a hyperbolic PDE, which basically means that there is a speed of information propagation in the problem because there's a speed of sound. And for hyperbolic PDEs, there is something called the method of characteristics. Method of characteristics. I believe this was also invented by D'Alembert when he derived this wave equation. I'm not 100% sure, but I think so. And I'm going to have a whole lecture on this. But what I want to show you is that when you have sine of something times cosine of something, you can use the trig identity, a really, really simple trig identity, which is sine of A times cos of B equals 1/2 sine of A plus B plus sine of A minus B. This is just a trigonometric identity. You can verify this yourself. But because all of our solutions have the form sine of something times cosine of something, I can essentially use those to write down the following. Essentially, my solution is going to be, u of x and t equals, how do I want to write this? I'm going to say this is equal to the sum from n equals 0 to infinity of that constant Cn divided by 2 times, now I'm going to have sine of this plus sine of this minus this. So that's sine of n pi over L x plus n pi over L ct. So I'm just going to say plus ct. And plus sine, I'll go back and we'll double check that I didn't mess anything up. N pi over L. And now it's this minus this. So that's x minus ct. And so this is really, really, really interesting. What this says is that because of this trig identity, sine of A times cos B equals 1/2 sine A plus B plus sine of A minus B, I can take these, and you can verify for yourself that n pi over L times x and n pi over L times ct give you this expression when you use this trig identity. What we find is that essentially our solution u of x and t is given by two, these are called waves, that are traveling in different directions. So x plus ct is a solution that is traveling in one direction. As time increases, this is kind of shifting my solutions. I think this is shifting my solutions. If time increases, then x has to be, negative to make this 0. And in this other part here is traveling in the other direction. So I'm just going to draw a little picture here. This is like a teaser for later, and I'm going to have a whole lecture on this method of characteristics, is that if I have some initial condition, essentially I have information traveling. This is x, and this is time. So if I have a little disturbance, that disturbance is going to travel in the right direction and in the left direction because of these two decompositions here. So I'm going to have a whole lecture going over the method of characteristics, which is how you can take these wave equation solutions here, and you can write them in terms of these kind of left and right traveling waves that give you kind of this interesting behavior, but I'll do that at a later date. Okay, good. We have derived the wave equation in the previous lecture. In this lecture, we solved it using separation of variables. We tied that solution to some physical intuition on a guitar string. So like literally what is the frequency of sound you hear as a function of the length of the string, the tension, the material, things like that. And we showed that using this trig identity, you can rewrite this solution in this intriguing form here, where I now have this kind of interesting anti-symmetric left traveling wave and right traveling wave. And so this is the basis of the method of characteristics, which will be another lecture for another day. All right, thank you.